Yogah Karmasu Kaushalam.
Hello, I am Dr. Kundan Tayde, and in this session we are going to discuss NMR spectroscopy. NMR means nuclear magnetic resonance. We have to focus on the nucleus, which should be magnetic, and the resonance should take place. Resonance is taking place when the two frequencies are matching. So, for being magnetic, the nuclei should have charge, and its I, that is the magnetic spin quantum number, should not be equal to 0. Also, the magnetic nuclei is having mass number which is not divisible by 4. The examples of the magnetic nuclei is enlisted in this table. You can see that hydrogen, carbon 13, fluorine 19 are the examples of the magnetic nuclei, whereas non-magnetic nuclei are having I is equal to 0 and their mass number is divisible by 4. Their mass number is divisible by 4. The example of non-magnetic nuclei is carbon 12, oxygen 16, silicon 28, etc. Further, the magnetic nuclei are classified into non-quadrupolar nuclei. When I is equal to 1/2, the nuclei are called as non-quadrupolar nuclei, and when I is greater than 1/2, then they are called as quadrupolar nuclei. Maximum value of I can be 9/2. In the periodic table you can see that various elements are there, and the maximum value of I may be 9/2. In case of the non-quadrupolar nuclei, we are getting the sharp peaks in the NMR spectrum, while in case of the quadrupolar nuclei, we are getting a broad signal. Nuclei abundance. You can see that hydrogen, fluorine 19, phosphorus, nitrogen 14, these are having very high abundance. Their percentage abundance is quite high. So another one is the low concentration nuclei whose abundance is very low. You can see that deuterium is there, which is the isotope of hydrogen. Its concentration is 0.015%. Carbon 13 is there, which is the isotope of carbon. Its abundance is 1.1%. Nitrogen 15 is there, its abundance is 0.37%. So, according to the abundance, the nuclei are classified as high concentration nuclei as well as low concentration nuclei. Furthermore, quadrupole nuclei, they are having the lower symmetry than the nuclei than 1/2 spin nuclei. Quadrupolar nuclei are having lower symmetry than the nuclei having I equal to 1/2, that is the non-quadrupolar spin nuclei. Quadrupolar moment varies with the nuclei, and it is measure of asymmetry. It is measure of asymmetry. Now, we have seen that in the previous slide, non-magnetic nuclei are the nuclei whose mass number is divisible by 4. The another classification we can see that if the nuclei is having even number of protons as well as neutrons, then they are non-magnetic nuclei. Because if even number of protons and neutrons are there, proton and neutrons are behaving like the magnets, and they have the tendency to pair up. You can see in the figure, the protons are coupled. Here the neutrons are coupled. If even number of neutrons and even number of protons are there, then they are coupling, and the net magnetic dipole moment is 0. There should be dipole moment, magnetic dipole moment in the nuclei, then only it is called as the magnetic nuclei. You can see that in case of the hydrogen, only one proton is there, so its S is equal to 1/2, as neutron is fermion, the proton is fermion. In case of this hydrogen proton, S is equal to 1/2. In case of the deuterium, which is the isotope of hydrogen, you can see that one proton is there and one neutron is there. So it is having S is equal to 1. Half is the value of S for neutron. this one is the neutron, and this one is the proton. So half plus half, it is having S is equal to 1. So I have told you that only charged particles are contributing to the magnetic dipole moment, and here we are saying that protons as well as neutrons are contributing to the net magnetic dipole moment. So the question may arise in your mind that neutron is neutral, so how it can contribute to this magnetic dipole moment? So this neutron is having some subatomic particles, that is called as up quark and down quark, which are having the charge, and because of the charge of these subatomic particles, that is the quark particles, the neutron is also contributing to the net magnetic dipole moment, though it is overall a neutral chargeless species. But because of the charges on the subparticles in the neutron, they are contributing to the magnetic dipole moment. Okay, so we will see next slide. Resonance frequencies of selected nuclei I have summarized here. You can see that the hydrogen nuclei is there. The applied magnetic field B0 in Tesla is given here. It is 7 Tesla, and the frequency corresponding to 7 Tesla is 300 megahertz. Okay, the gyromagnetic ratio of this hydrogen nuclei is given here. Then we will focus on the carbon 13. You can see that at 7 Tesla, the frequency corresponding to the carbon 13 nuclei is 75 megahertz. As the gyromagnetic ratio is 1/4 in case of C13 compared to the proton, the frequency is also 1/4. You can see that the gyromagnetic ratio in case of hydrogen is 267.53, and the gyromagnetic ratio of your C13 nuclei is 67.28. So the ratio is 4:1. Further we will see the Boltzmann distribution law. We know that it gives idea about the population of the states. Degenerate energy levels are there, but when these degenerate energy levels are exposed to applied magnetic field, then the nuclei distribute themselves between the lower energy level and higher energy level. Lower energy level is always having the higher population, and higher energy level is always having the lower population. The energy difference between the two energy level is given by delta E. Now you can see that here I have taken one example, that the population of E1, that is lower energy level, is 505, and the population of the higher energy level is 495. The population difference delta P is equal to 10. So we require 5 transitions for making the population of the two states equal. But the population of two states should never be equal, otherwise there will be a saturation and the signal will vanish. So there is a population difference, but here there is possibility of 5 transitions to make the population equal. If you increase the energy level difference, if number of transitions of the nuclei increases, you can see that the population of E1 in this second case, E1 star is equal to 600, and the population of the higher energy state E2 is P2 star population state. Population of the E2 state is 500, so we can see that the population difference is 100. So at least we require 50 transitions to make the population of two states equal. So from this figure we can conclude that as delta E increases, the population difference increases. As a result, the intensity of the spectral line increases. Here intensity corresponds to height of the peak. Okay, So delta E increases, delta P increases, that is the population difference increases, and intensity of the peak increases. Then we will talk about the sensitivity of the nuclei as well as the instrument. The sensitivity of the nuclei depends on its natural occurrence or natural abundance. You can see that hydrogen and fluorine 19, these are having the high concentration in the nature, and when natural abundance is high, very less sample is required and very less time is required for recording the NMR spectrum. So abundance and gyromagnetic ratio should be high. So we can say that the sensitivity is high in case of that nuclei. In case of instrument, the sensitivity depends on the magnetic field you are applying or the frequency you are using, radio frequency you are using. You can see that 200 megahertz frequency instrument is less sensitive than 600 megahertz instrument. Here the frequency is directly proportional to the applied magnetic field. We are having the equation nu is equal to gamma, that is gyromagnetic ratio, divided by 2 pi into B0, that is the applied magnetic field. So therefore this nu is directly proportional to the gyromagnetic ratio. Now delta E is equal to h nu. So we can say that from the previous slide, that is delta E is directly proportional to delta P, is directly proportional to intensity of the peak, and from this current slide we can say that delta E is directly proportional to the frequency, it is directly proportional to the gyromagnetic ratio, which in turn directly proportional to the population difference between the two energy states, which is directly proportional to the applied magnetic field, and which is in turn directly proportional to the effective magnetic field, which is actually experienced by the nuclei. Your experienced magnetic field, which is experienced by the nuclei, might be different from the applied magnetic field. Now we will have glance towards the instrumentation of NMR. You can see the block diagram of this instrumentation of NMR. It consists of large magnets. These large magnets are producing the homogeneous magnetic field. Homogeneous magnetic field should be maintained. If homogeneous magnetic field is not maintained, then the protons of same type in a different part of the sample will precess with different frequencies and your signal will become broad. We don't want broad signal, we want sharp conclusive signal. So we have to maintain the homogeneous magnetic field. Furthermore, sweep coil is there. You can see that sweep generator is there. With the help of the sweep generator, we can change the magnetic field over a small scale. See, we have to maintain the homogeneous magnetic field, but we can change the magnetic field over a small scale, over a small range by using this sweep generator. Radio frequency transmitter is there, which is producing the radio frequency waves. Then radio frequency receiver is there, radio frequency receiver, and amplifier is there. Okay, the superconducting coils are needed to be cooled by liquid helium. This you have to keep in mind. Sample tube is there. You can see that the spinning sample tube is shown here. This is the sample tube. It is also spinning in this magnetic field. Now we will see one by one NMR tube and the solvents used in NMR. So NMR tube is available in different dimensions. Generally its diameter is 5 mm, its length or height is 15 to 20 centimeter. You can see that it is having rubber sealed plug. because we are spinning the sample is dissolved in suitable solvent. You can see that CCl4 can be used. It is not having any proton, so it will not interfere in the proton NMR spectrum. But instead of CCl4, we are generally preferring deuterated solvents. If we are not using the deuterated solvent, if we are using the solvent as such without replacing the hydrogens of the solvent by deuterium, then we will get a overwhelming peak of the solvent. So to avoid swamping, overwhelming peak by the solvent, we have to use deuterated solvents. Deuterium is giving its signal in a different frequency region, so we don't have to bother about it. It will not interfere in the proton NMR spectrum. So to avoid the swamping, overwhelming by the solvent, we have to use the deuterated solvents. Example is CdCl3, in which the hydrogen of chloroform is replaced by deuterium. To stabilize the applied magnetic field strength by deuterium absorption of solvent, we can use deuterated solvent. Sometimes the superconducting magnets are showing drift. For the internal calibration, then we have to use this deuterium. This deuterium is maintaining magnetic field homogeneity. If any fluctuation, if any drift is occurring in the superconducting magnets, we have standardized the instrument with respect to deuterium, so that drift of superconducting magnets will not allow the disturbance of magnetic field homogeneity. Then you can use the deuterium lock signal, field lock. Lock on the deuterium signal avoids the use of internal standards. You are using the internal reference standards such as TMS, or if you are using DMSO, DMSO is giving the residual peak due to the proton at 2.54 ppm. In case of DMSO, we don't have to use TMS. The DMSO residual peak itself working as a reference standard. This you have to keep in mind. In case of CdCl3, we are getting the residual peak at 7.26 ppm due to the small quantity of chloroform CsCl3 left. In case of benzene, in case of deuterated benzene, in case of deuterated DMSO, we don't have to use TMS, that is tetramethylsilane, as internal reference standard. Benzene, the residual peak due to benzene as well as the residual peak due to DMSO, they are working as internal reference standards. So use the deuterated solvents rather than CCl4. Two types of NMR methods are possible here. Field sweep method is there. Name itself suggesting that we are changing the field. To sweep means to change, to vary. In this method, the radio frequency signal is held constant and we have to change the magnetic field over a small range, over a small scale. So if you consider ethanol, you are changing the magnetic field, your radio frequency signal is constant. So first the OH peak will appear, because whatever the magnetic field you are applying, that will be experienced as such by the OH proton, because OH proton is highly de-shielded, oxygen is highly electronegative. It will remove the electron cloud nearby to the hydrogen of OH and the proton will be de-shielded. If the proton is having high electron density nearby to it, it is called as shielded proton. You can see that the CH3 protons are quite shielded. The magnetic field due to the electrons of these CH3 protons will oppose the applied magnetic field. So we have to apply the high magnetic field as compared to OH. So first the OH peak will appear, then CH2 peak will appear, then CH3 peak will appear, and at the last the signal for TMS, tetramethylsilane, will appear as the protons of TMS are highly shielded. There are 12 equivalent protons, and it will give the signal at the extreme position. Then linear sweep method is there. In this linear sweep method, the magnetic field is held constant and the radio frequency signal is swept. So you can see that the CH3 will precess with very small frequency. So at the lower frequency, this CH3 is precessing. That's why its signal will appear first, then the signal of CH2 will appear, then the signal of OH is appearing in the NMR spectrum. If you will consider TMS, then first the signal of TMS will appear, then of CH3. In case of the ethanol, CH3, CH2, and then OH. Which are the different internal and external standards used in NMR? We have just discussed, and it is very popular one, that is the TMS, but the countdown is there with you. You can enlist some of the internal reference standards or external reference standards which can be used in NMR spectrum. Please answer in the chat box. TMS is already done. So beside TMS, which are the different reference standards used? We have seen that TMS is used. So this is the NMR spectrum of ethanol, that is the pure ethyl alcohol, absolute ethanol. You can say that here the scale is from 0 to 10 generally, and it is in delta. It is a delta scale, chemical shift scale. Its unit is ppm. So you can see that at 0 position we have taken TMS. In case of the absolute ethanol, how the coupling is taking place, we know that. We are just simply applying the n+1 rule. On the neighboring atom, neighboring carbon or neighboring atom, how many protons are there? +1. So CH3, CH2, OH. Nearby to CH3, there are 2 protons on the carbon. So you can do 2 plus 1. 2 plus 1 is 3. So CH3 will give triplet. Nearby to CH2, CH3 is there, means 3 protons of CH3 are there, and at the another side OH is there, which is having 1 proton. So in case of absolute alcohol, absolute ethyl alcohol, that OH proton will also couple with the CH2 protons. Spin splitting will take place. The signal can be calculated like this. Signal is equal to n+1 into m+1. So S is equal to 3 protons from CH3 plus 1 into 1 proton from OH plus 1. So 4 into 2 is equal to 8. So we are getting the 8 lines, 8 signals, we can say. If OH is not interacting with the CH2, the proton of OH is not interacting with the protons of CH2, then we are simply getting a quartet whose intensity is 1:3:3:1. But here, in case of the absolute alcohol, you have to keep in mind that it results in succession of 1s to 3s to 3s to 1 doublets, or you can see that we are getting the peaks like 1s to 1s to 3s to 3s to 3s to 1s to 1. The result image of the signal I have shown here, you can see that here 1s to 1, 1s to 1 is there, and this is corresponding to 3 3 3 3. So the splitting results into succession of 1s to 3s to 3s to 1 doublets. Ethyl alcohol containing 1% formic acid. If your alcohol is impure, it is having some acidic or basic impurities, then your OH proton is not coupling with the CH2 proton in ethanol, because there is rapid exchange of proton of OH with proton of the acid. So it is not residing on the heteroatom, that is OH, oxygen, for a long time. It is continuously exchanging. That's why it is not available for coupling, and we are getting singlet for OH, we are getting quadrate for CH2, and we are getting triplet for CH3. The signal is shown here. Here is hydrogen bonding shown. The hydrogen bonding is present in ethanol or alcohols is shown here. You can see that we can break or reduce this hydrogen bonding by addition of carbon tetrachloride. If you are breaking the hydrogen bonding, then you can see that the peak of OH is shifted to upfield. First signal is of TMS, which is taken as reference. Then the second signal is of triplet due to CH3. Then the OH singlet is there, and then the quadrate is there. This is happening because of addition of the carbon tetrachloride, which is reducing the hydrogen bonding between the alcohol and water molecules. Now, if you have a glance at the NMR guidelines for ACH journal, then you can see that I have told you, if you are using the deuterated benzene, for the deuterated benzene, the peak is appearing at 7.15. It is treated as residual internal for the NMR spectrum, and it is because of this C6D5H. A very small quantity of protonated benzene is left, though the benzene molecule is deuterated, and it is giving the signal at 7.15. Here you can see that at 0 there is no TMS. Similarly, when you are using DMSO, then due to the DMSO we are getting peak at 2.54. You can use that peak as internal standard, and you don't have to add TMS additionally. Tetramethylsilane, there is no need to use tetramethylsilane again. Next slide we will see. This is the NMR spectrum of phosphorus containing compound. We are using orthophosphoric acid, which is the deuterated orthophosphoric acid in 85% D2O, that is the heavy water. In this case also we are using the standard, but this is the external reference standard. The TMS is internal reference standard, that you have to keep in mind, and orthophosphoric acid, which is deuterated, which is prepared in D2O, its concentration is 85%. This is the external reference standard, because if you are using it as internal reference standard, it may interact with your sample, so don't use it as internal reference standard. Next we will see the nitrogen NMR spectrum. So where we are using this nitrogen NMR spectrum? In case of the high energy materials, you can see that Most of the high energy material, that are the explosives, are using the compounds which are containing nitrogen. So many times the reviewer is asking for the nitrogen 15 NMR spectrum if you are working on the high energy materials. You can see that methyl nitrate, its 90% solution in CdCl3 can be used as reference standard, or you can use ammonia, that is liquid ammonia, as reference standard. The conversion for nitrogen 15 and nitrogen 14 is recommended by the IUPAC is shown here. If you have glance at the spectrum, you can see that the spectrum of nitrogen 14 is broad. It is resulting into a broad peak because nitrogen 14 is having I is equal to 1, and when I is equal to 1, it is called as the quadrupolar nuclei, and quadrupolar nuclei are resulting into broad peak, while you can see that the peak due to nitrogen 15 is very sharp. Okay, so methyl nitrate, as well as, which is 90% methyl nitrate in CdCl3, and the liquid ammonia can be used as reference in nitrogen NMR. Now, what about the different internal standards used in NMR when you are using water as a solvent? So, DSS and DSA are the example. So, what is DSS? That we will see. DSS is sodium trimethyl silyl propane sulfonate, and it is organosilicon compound with the formula which is shown here, depicted here. You can see that the IUPAC name of this DSS is given, that is sodium 3 trimethyl silyl propane 1 sulfonate. So basically it is sodium salt of trimethyl silyl propane sulfonic acid. It is a white powder which is soluble, white solid powder which is water soluble, and it can be used as reference standard in case of the proton NMR spectroscopy whenever you are using the aqueous solutions. Its structure is shown here. This DSS is relatively insensitive to pH, that is the advantage. But there are some problems associated with the DSS. The DSS can interact with the cationic peptides so that it can diminish or vanish its value for such studies. So whenever you have to study the cationic peptides, you have to use DSA instead of DSS. DSA is also a new internal standard whenever you are using the aqueous solutions for your NMR study, and DSA do not suffer such problem. They do not wash out or do not dealt with the do not compromise the cationic peptide signals. Okay, also I have mentioned, don't use any internal reference, simply use the field frequency log. I have told you the field frequency log, if you are using, that is the deuterium log, then there is no need to use any internal or external reference standard. Field frequency log itself working as a reference. Okay, now why the scale in NMR is reference scale? It is not a absolute scale. Okay, so we are using the relative difference scale rather than the absolute scale. Why it is so? We will see. In a very large applied magnetic field, if very small change in frequency is taking place, we are applying a very large magnetic field. The frequency of that large magnetic field is megahertz. Mega means which is 10 raised to 6 hertz. 1 million hertz. And the change is taking place that is in few hertz. So it is very difficult to locate this small change in few hertz in the relatively large magnetic field with high frequency of million of hertz. Also, the signal in case of absolute scale are so cumbersome, they are so complicated, they are so closely placed, they are not well resolved, so that we cannot get a proper conclusion. They are very closely placed. The scale becomes very complicated, it becomes very cumbersome, the absolute scale. Same signal appear at different values if you are using NMR spectrum of different magnetic field strength. Suppose XYZ person is recording the NMR of ethanol on 300 megahertz instrument, and another person is recording, PQR person is recording the NMR spectrum on the instrument whose frequency is 500 megahertz, then it is possible that the signal will appear at different positions if you are using the absolute scale. For 300 megahertz, the signal may appear at 3 delta, then for 500 megahertz, the same signal may appear at 6 delta or at some different value. I have just taken it for example. It might be the different case, but for the same molecule with instrument of different frequencies, you are getting the peaks at different positions. Protons, same protons resonate at different frequencies depending on the strength of the applied magnetic field and the radiation you have used. So to avoid this confusion, a new parameter is introduced, that is the chemical shift, which is independent of the applied magnetic field. You can see that here I have taken the example of chloromethane, which is simply methyl chloride. It is having 3 protons. You can see that when you are using the instrument of 400 megahertz frequency, then the difference between the signal of TMS and chloromethane protons is 1220 hertz. But when I am using the instrument of 500 megahertz frequency, you can see that the difference between the TMS and the chloromethane proton signal is 1525 hertz. The delta value, that is the chemical shift value in ppm, is equal to this difference in the difference of the sample from the TMS value divided by instrumental frequency. If you divide 1220 by 400 megahertz, you will get 3.05 ppm. If you are dividing 1525 by this 500 megahertz, then you are again getting 3.05 ppm. But at the absolute scale, you are getting different positions. You can see that for 400 megahertz, the position of the proton signal is different, and for 500 megahertz instrument, the position of the proton signal is different. But whenever we are using this chemical shift scale, then we are getting the same value, that is 3.05 ppm. You just divide this 1220 by 400 megahertz, and you can divide the 1525 by 500, you will get this value only, 3.05 ppm. So it is better to use the chemical shift scale we are not going for the magnetic field strength scale. Okay, here I have enlisted some nuclei. The isotope is there, hydrogen, deuterium, tritium, like this, and various nuclei are there, fluorine, phosphorus. Here the Larmor frequencies in megahertz are correlated with the Bruker field strength, that is the magnetic field strength. This is for particular Bruker instrument NMR, which is whose make is of Bruker. So they have given this table. From there I have taken Larmor frequencies are correlated with the applied magnetic field strength simply. Frequencies in megahertz and magnetic field strength is in Tesla. You can see that for 300 megahertz instrument, the frequency for proton is 7 Tesla. Magnetic field is 7 Tesla. Then for frequency of 400 megahertz, the field strength is 9 Tesla. For 500 it is 11.75 Tesla for 500 megahertz frequency. Now reference scale. What is the advantage of reference scale? We can see that whenever you are using the reference scale, the NMR spectra becomes resolved. Reference scale is relative differential scale. Herein TMS signal is considered as 0 and the difference of the signal of the sample from the internal reference, that is TMS, is recorded. Suppose you are using the instrument, suppose the numerical difference between 1 million hertz and 1 million and 10 hertz is 10. So rather than plotting the million scale, you just plot the difference scale. The difference is of 10. So you plot the scale from 0 to 10. Rather than using the million scale, which is quite complicated, we can go for the 0 to 10 scale, which is the difference between these two numerical values. Here, because of this differential scale, we got the resolution. Furthermore, we have seen that chemical shift is independent of the applied magnetic field. You can see that if you are using the instrument of 300 megahertz frequency, its magnetic field is 7 Tesla. You are using TMS as the internal reference standard. Then the absorption for TMS will be at 300 megahertz, that is 300 million hertz. It is one and the same thing. And the absorption signal for the sample will appear at 300 million and 300 hertz. So the signal for TMS is 300 million hertz and the signal for sample is 300 million and 300 hertz. So if we are taking the difference between the two, it is 300 hertz. The difference between the reference and sample signal, it is 300 hertz. We can divide this 300 hertz by the instrumental frequency. The instrumental frequency is 300 million hertz. So you can see that 300 hertz divided by 300 million hertz is equal to 1 by 1 million, and it is called as 1 parts per million, means it is called as 1 ppm. If you are taking 500 megahertz instrument, then the TMS signal is at 500 megahertz, means the TMS signal is at 500 million hertz, or it is at 500 megahertz. The sample signal will appear at 500 million 500 hertz. So if you will take the difference between the two, the difference is of 500 hertz. So just simply divide this 500 hertz by this 500 million hertz, you will get again the 1 by 10 raised to 6, that is the 1 ppm. But we have to keep in mind, in earlier case the frequency was 300, in this case the frequency is 500 megahertz. So the frequency of the sample will increase proportionally. The frequency of the sample is also increasing proportionally to the applied magnetic field, to the applied radio frequency. Okay, here I have shown the NMR scale. It is ranging from 0 to 10 generally. The delta value, delta is for chemical shift, it is in ppm. Okay, TMS signal you are taking at 0 ppm. It means that if you are using 300 megahertz instrument, the value of TMS is 300 megahertz, and this value at the high field, sorry, at the down field, you will get due to the 300 megahertz plus frequencies. Okay, we have seen that. Then field sweep method. Field sweep method, we know that we are sweeping the field, magnetic field, we are keeping the radio frequency constant, and B0 is swept. We are continuously changing the B0. The first signal will be of OH. In this case, because the proton of OH is highly shielded, oxygen is highly electronegative, it will fetch the electron density nearby to this proton. That's why this OH proton is deshielded, it is not having sufficient electron density nearby to it. So whatever the magnetic field is applied, that will be directly experienced by this OH proton. And this CH3 protons are shielded, they are having high electron density nearby to it as compared to OH, and no doubt the protons of this tetramethylsilane are highly shielded. So whenever you are using field sweep method, first signal will appear because of OH, second signal will be because of CH2, then because of CH3, and at the last the signal will be of protons, will be because of protons of tetramethylsilane. 12 equivalent protons of tetramethylsilane. You know that tetramethylsilane is the internal reference standard, it is having 12 protons. We have to use very small amount of tetramethylsilane. Then it is volatile, so you can remove that TMS from the sample, you can recover your sample. So NMR is non-destructive technique of analysis, let it be. But it is not essential to always use TMS. We have seen that. We have seen a number of alternatives for TMS. Deuterium lock method, then use of residual solvent peak as a reference, internal reference standard. Then we have seen various internal reference standard used for aqueous solutions. Okay, now we will move to the trick to remember chemical shift values. So when the hydrogen is attached to sp3 carbon, its chemical shift value may range from 0.5 to 2.0. If the hydrogen is attached to sp3 carbon, but it is also attached, the carbon is attached to electronegative atoms, some electronegative atom such as oxygen, nitrogen, etc., then the value of that proton may be in the chemical shift range 2 to 5. If your hydrogen is attached to sp2 carbon, then your chemical shift value may be in the range 5 to 8.5. For aldehyde, the chemical shift value is probably in the range 8.5 to 10. If your proton is of carboxylic acid, COH proton is there, or phenolic OH is there, then its value may be beyond 10, means it may have negative delta value. In many interviews this question is asked. So COH is giving the negative delta value, phenol proton is giving the negative delta value. Some of the examples I have taken 18 aniline, it is also giving the protons in the ring current are giving the negative delta value. In case of the 7 para cyclophane also, for these protons we are getting the negative delta value. The basic concept is of shielding, deshielding, anisotropy. Many concepts are there which are responsible for this negative delta value, but you have to keep in mind generally the acidic proton and phenols are giving the signal at very downfield side. Okay, in case of the hydrogen which is attached to sp carbon, we get the signal of chemical shift between 2 ppm to 3 ppm approximately. Now we will see the coupling constant. It is the distance in hertz between adjacent peaks of the multiplet, and it is measure of effectiveness of the spin-spin coupling or spin-spin splitting, and it is called coupling constant, which is denoted by J. Coupling constant J is measured in hertz, and it is generally in the range 0 to 18 hertz. For a particular multiplet, the distance between the peaks, splitted peaks, are identical. Here I have taken one example. Suppose you have recorded your NMR spectrum on the instrument of 300 megahertz frequency. You are getting a triplet and whose peak positions are given here: 0.90, 0.95 and 1.00 ppm. So the coupling constant J in hertz is equal to delta P in ppm into instrumental frequency. So J is equal to, you can take the difference in the peak position, 0.95 minus 0.90, just multiply that difference by instrumental frequency. So you can see that the difference is 0.05 in this case. Just multiply it by 300, so you will get 15 hertz. Simple is the thing. Carbon 13 NMR satellite. See, I have told you carbon 13 is NMR active. H1 is also NMR active. If you are having highly symmetric molecule, and in that symmetric molecule you are having H1 as well as C13, then this carbon 13 NMR satellite peaks are observed. Carbon satellite are small peaks that can be seen shouldering the main peak in the proton NMR spectrum. On either side of the main peak, these satellite peaks are observed. In proton NMR, these peaks are not the result of proton-proton coupling, but they are because of the coupling of H1 atom with the adjoining C13 atom. These small peaks are known as carbon satellite peaks. As they are very small, they appear around the main peak of main H1 peak. Sorry. That's why it is called as satellite. Carbon satellites are small because the abundance of C13 is very low. We have already seen that the abundance is approximately 1.1% of the atomic carbon content of carbon. The rest of the carbon atom are predominantly NMR inactive, which is carbon 12 isotope of carbon. Carbon satellite always appear as an evenly spaced pair around the main H1 peak. This is because they are the result of 1% of the, or approximately 1.1% of the C13 atoms coupling to the adjoint H1 atom. Note, if the main H1 peak has proton-proton coupling, and then each satellite peak will be the miniature version of the main peak and will also show this H1 coupling. We will take the example. If the main H1 peak is a doublet, then the carbon satellites will appear as miniature doublet on both the side of this main doublet, which is because of proton coupling. Carbon satellites and spinning side bands, we have seen that the NMR tube is spinning. spinning side bands are because of that spinning of the NMR tube. These carbon satellite peaks and spinning side bands should not be confused with the impurity peaks. You might think that these are the impurity peaks. No, they may be carbon 13 NMR satellite peaks, or they may be the spinning side band peaks or spinning side bands. The example I have shown here, you can see that the steel beam is there. Steel beam is highly symmetric. 1,2-dichloroethane is there. If the adjoint H1 and C13 atoms are there, then here there is possibility of NMR satellite peaks. Then interpretation of NMR. We have to learn the interpretation of the NMR spectrum. A simple example I have taken here. You can see that the signals are integrated. You have to measure the height of the integration. With the scale you can simply measure the height of the integration. Total number of integration units in case of the first signal, that is signal A, the integration unit, number of integration unit is 54. In case of signal B, the number of integration unit is 23. In case of signal C, it is 33. So total number of integration units is addition of 3. It is 110 units. We know that total 10 protons are there in this molecule. As we can have glance at this molecular formula, we come to know about the number of protons. So basically 10 protons are there. So divide the total number of integration units, that is 110 units, by the number of proton. 10 protons, we are getting the value of units per proton. So 11 units per proton, values of 10. Now just divide this number of integration units, each number of integration unit, by this units per proton. Divide 54 by 11, you will get 4.9, which is approximately equal to 5. So this is saying that 5 protons. This signal is because of 5 protons. Then similar is the case with signal B and C. We come to know about the number of protons. The signal corresponds to how many number of protons. Okay, and we can correlate it so that we can determine the structure of the compound. This NMR spectroscopy is quite sensitive. It can detect the signal up to 7th decimal point with accuracy. We are generally sticking up with 2 decimal points or like that. Research relevance of NMR, I have told you, you don't have to record the NMR spectra of complexes, especially complexes of transition metals. The NMR spectrum of transition metal complexes is broad, similar to the quadrupole nuclei. Okay, so it is better to study the complexes, metal complexes, with UV visible spectrophotometry as well as IR spectrophotometry. For diamagnetic metals, we can record the NMR spectrum of the complexes. In case of the lanthanides, even with the paramagnetic complexes, we are getting a sharp peak, but here in case of the transition metals, which are the paramagnetic transition metals, we are getting the broad peaks. So for that, UV visible spectrophotometry and IR spectrophotometry are the better options. You can use this NMR spectrophotometry for structure determination, which is the very basic one. You can use it for molecular recognition studies. Sometime the OH signal or NH signal is shifting or it is getting vanished. When we are studying the molecular recognition of anions, the host gas study we are doing, then changes in the signal can be studied with NMR. Real-time analysis is possible. One simple example I would like to give. You can couple this NMR with the solid phase extraction method, SPE. Real-time analysis can be done. So during the real-time analysis, if some hazardous compound is forming, we can stop that reaction. We will not allow that reaction to proceed further. real-time analysis is also possible. You can couple SPE with NMR or many other techniques. Hyphenation means coupling of two or more techniques so that we can get the advantage of each technique. It is also called as hybrid technique. We have to focus on the residual solvents in the NMR spectrum. Suppose you have prepared your compound in DMF. In your NMR spectra, which you have recorded in DMSO, the residual peak of DMF may left. So one research paper is there on that residual solvent peaks. I have given the bibliography in which that reference peak is reference paper, research paper is mentioned, which tells you about the different residual solvents, different residual solvent peaks which are left in the NMR spectra. So for the further research relevance of NMR, I suggest you to explore these two sites. For assessment of your learning level, I have created one simple Google form questionnaire. So I request you to fill this questionnaire. Whatever material I have used for preparing the video is summarized here in the bibliography. The bibliography is mentioned. I suggest you to use following references for further reading. The YouTube videos made by some peoples like Yogi Joshi and many more peoples are quite good. The bio one channel is there, so they are making very good YouTube videos. You can explore them so that you can get a deeper insight to the spectroscopy, which is must. Thank you very much. Once again, I would like to thank Honorable Director of UGC HRDC Gujarat, Joshi sir, as well as Honorable Course Coordinator in Chemistry, Dr. Wasawa sir, and his whole team. Thank you very much for giving me this opportunity.
Thank you very much, sir. It was very nice and informative session for all. Thank you very much once again.